Roger Wang is an assistant professor in the Department of Civil and Environmental Engineering at Rutgers University. His research focuses on developing numerical models to connect big data and decision making in coastal engineering, natural hazards, water resources, and renewable energy systems. Roger, thank you so much for taking the time.
Thank you, Joe, for taking me.
So, to start, could you tell the audience a little bit about your research and what you're working on?
Yes, currently we are working on different directions. I think we are focusing on using the emerging AI technology to support data collection from sensors and also try to develop numerical models to support decision makings. So AI will be the link between every component in my research. More specifically, I think we are working on coastal issues. Currently, the coastal is facing different challenges. Humans are developing the coastal area. For example, we are building new artificial islands. If you think about the palm tree islands in the Middle East, Dubai, and if you think about the large port or airport development in Asia, so these coastal projects could really change the coastal environment. In the meantime, I think back to the United States, we are also working on different offshore wind projects. These projects could also change how we interact with the coastal marine environment. I think we are working on many different areas, so I'd love to talk more about those things.
So you mentioned data collection from sensors and the AI is helping you do that. What are the sensors collecting and where are they?
Yes, now we are currently using a very specialized camera. It's called a hyperspectral camera. So usually if you, like a cell phone, if you take a photo using your cell phone, it's actually three images every time you take a photo because it's RGB. So in each channel you have a photo. However, the specialized hyperspectral camera, it has 113 channels. So if you take a photo that generates 113 images, every 5 nanometer of light wavelength will going to have this photo. So this camera can tell very nuanced color change. I think most time this is used in agriculture because if there's a drought, if there's a disease of the plants, of the crops, then this camera can tell very early that whether there's a problem with the crop and predict how much yield at the last of the year. So we are using this camera to monitoring the environmental. For example, we are looking at the sediment suspension in the coastal and coastal waters and also in the lakes. We are also trying to monitor if the algae bloom happening, whether we can predict that using the color of the water. So these are something we are uh, working on. In the meantime, we will also work on other different things. For example, we are quite interested in the microclimate in the urban area. Traditionally, the weather stations are positioned in the rural areas because the weather station try to have less impact of like traffic or other human interference. So what we are working on is uh, trying to develop some sensors inside of the city. But it could be very expensive if you build new sensors in the city. So we are trying to use existing infrastructure. For example, we're using optical fiber, which is the fiber you use, the cables you use to connect the internet from every home. So we can hear the raindrop hit these cables, and from that we can measure in the city what's the precipitation look like or the rainfall look like over the city without investing new infrastructures. Other things we are looking at is how the 5G towers, we have new 5G towers which millimeter wave 5G. We found that the signal from one base station to another station actually very sensitive to the weather. So if in the future we have a very well coverage of the city area, um, we can just estimate how the signal from one base station to another base station attenuates. If attenuate more, that which indicates there's a bad weather, and using this, we can have a very good coverage of the urban weather. So that's something we are currently working on.
So you mentioned that this data that's collected is also going to help with decision making. How does that
Mm.
happen, and what does your research look like in that regard?
Yes, we one example I would like to use is the flood response or flood resilience. Um, Currently, we are using the ChatGPT, using the large language model, which is a very good interface. It can translate citizens' question or decision makers' questions into actionable uh, it can so any question asked from the public, it's um, sometimes very difficult to uh, match with the information from our model. For example, if you are asking what's the flooding risk for this neighborhood, um, the modeler sometimes has difficulty to explain. For example, we use the return period, which actually is the probability of a flooding in this area. How to explain, translate this expertise, the jargons, terms to the public. I think ChatGPT can fill the gap. We already submit a paper that can translate such public answers into some numerical functions, and these functions call or search online to find the relevant information. And then feedback, we need ChatGPT to translate again to the plain language answer to the public. Using this, we close the loop between the modeler, between the decision maker, between the stakeholders, and we link everyone together using on the same page.
Yeah. When it comes to these connected systems between the data collection and the decision making, do you envision that more cities and states will adopt kind of data collection infrastructure to monitor the environment and the built environment?
That's, I think, still quite challenging now. For example, we develop a social media-based flood monitoring. We use Twitter, now it's X, to extract flood information. However, there's quite some uncertainty of this information. For example, is if someone tweets, "Oh, there's a flood in the main street here," we don't know which town, we don't know which city, and humans are so uncreative to name the streets. So the main streets everywhere, the first streets, and like Broadways, so common. So how do we determine the real location of the flood? I think, given this uncertainty, I think we found that could be some niche. For example, we can monitoring the volume of the tweets the citizens are talking about on the platform. For example, this is how much people talk about the preparedness for this hurricane. And then after that, when the hurricane landfall, and we can see there's a peak of the witness of the flood scenes. And then after the peak, we found, oh, there's another peak. People start to talk about the recovery from the flooding events. I think if collectively we can tell what's the hot topic, what's the focus of the society now in terms of the recovery response to these flood events. However, if a geolocation, I think is still challenging. And when we show this kind of data to the government agencies, they still reluctant to see this data has so much uncertainty on spatial information. But the temporal probably that's some useful, but still we are trying to convince more and more agencies that could be useful for uh, mm, the emergency teams in the field.
Yeah. Earlier, when you were talking about coastal applications, you mentioned sediment suspension.
Mm.
What is that, and could some of those applications also look at like sea level rise, or how do you think about that?
Yeah, sediment transport actually is quite important for the geomorphology, which means that if the river is carry a lot of sands downstream, so the upstream will lose the sand, and then there's could be erosion problems. So the river banks could change, and it will damage the neighborhoods, and maybe someone's backyard will reduce, something like that. So and also it can with the more sediments, it accumulate at the harbor, so the ship has the difficulty to move into the rivers, and then this could be navigation issues. And of course, there's a huge ecological problems if no the sediments actually come with nutrients. If somehow the balance is broken, and then the ecosystem will not be stable anymore. So a lot of issues like that. What we are curious is that people use satellites to look at how much sediments in the river, in the lakes. However, they don't accurately test in the lab. They just use the empirically. So they say, oh, this color that's looks darker. Maybe this means more sediment there. What we are trying to do is in the lab, we want to accurately test whether this is true or not. If you train such a model to tell this is how much sediments based on the watercolor, is that reliable? How much uncertainty is there? So we try to um, maybe um, correct people's vision on this, and maybe provide a better formula, better guidance how to use the satellite more reliably.
So could you sync the sensors that you're using with satellites and have them uh, either communicate or reconcile data in between them, or how does that work?
Yeah, that's another field. It's actually quite challenging. It's people are trying that for different satellites because satellite has several issues. One issue is the revisit intervals, which means the frequency of the scanning. Like the most famous satellite, which is the Landsat, every 14 days it revisits the same place. It's not like okay, you have a big brother looking at you from the space. It's not like that case. It's always orbiting around the orbit. So it's not um, how do you use such a low frequency of the scanning to inform the landscape changes? That could be a challenge. So people try to use different satellites because combining different satellites, they could have a better frequency. These satellites just pass by, but another satellite come here. So, however, they have different orbits. They have different cameras, different sensors. They collect different information. How to they also have different accuracy. So how do you reconcile those things? There's a new method called data fusion. They're either traditional method or there's maybe artificial intelligence based methods. People are developing those methods, but it's still challenging. So it's no one has um, the answer to all the questions. So, but scientists are working on this. I think that's still a very hot topic right now.
Yeah. Well, so the sensors that you use, those are pretty close to real time, right?
The sensor, yeah, it's well, it's not like the video cameras. It's video camera usually has 30 hertz, but our sensors because it's we need to record it a lot of images. So that's the updating frequency actually is lower. But there's a new camera. I think they could do a better job now. Yeah. If you see real time, yes, it can works in real time. Like maybe every second you have several like 10 images. Yeah.
So what do you see as the future of this research? What's on the horizon for you right now?
Yeah, currently we are imagining how we can 3D reconstruct the information we collected from videos. For example, if recently we just finished a study, there's a dam collapse in central Michigan. Luckily, there's a guy who just stand besides the dam collapse and using iPhone to record everything. And we get permission to use that videos. We use geolocation, the elevation map. So using some local information, we can reconstruct the 3D dam collapse process from just the 2D video images. It turns out to be the only quantitative data in this field, and several companies approach us and say, "Hey, we really need such a data because we want to understand at the beginning, at the very beginning, how quickly the dam collapsed, which can be a very important to find out the reasons of the dam collapse and attribute the responsibility of this collapse. They want to build a better model for that. Those public data is only after the dam collapse that they measure how big the gap is at last. It's not at the beginning. So I think we are trying to develop more and more using AI, using better sensors that try to reconstruct the 3D world from the 2D data.
Wow. Well, Roger, thank you so much for taking the time to share your research and to share your insights. And I hope we can continue the conversation down the road.
Thank you very much, Joe.